we will start by having our 5 panelists give a brief, hopefully, introduction to themselves, what they've worked on specifically in the space, and what they would like to see done, if not by themselves, then by others in the future for tokenization. Kris, go for it.
Hi. I guess I'm the them that Yuval Pinter was talking about in his keynote. I work currently at Cohere on model pre-training. Before that, I was at Google DeepMind. Most recently there, I was also working on Gemini pre-training. Even before that, I did my PhD at the University of Cambridge. I've worked on many different things, sort of in the NLP ML space, particularly about tokenization. I've thought about composable character level representations, and also evaluation practices taking into account tokenizer ambiguity. What would I like to see in 5 years? Oh, that's a very good question. I would like to see, and I think this might be a controversial statement, but I believe that there are better tokenization algorithms out there. I think there are a few cases and domains where current tokenization is applied, but doesn't really fit the bill very well. And in particular, I think code performance is something that many large models highly prioritize. But I've seen with my own eyes the impact that tokenization can have on code performance. And I think understanding how we best tokenize code is something that is like crucially important, at least for my company's interests in the next 5 years.
Perfect.
Thanks, Kris. Hey, I'm Sander. I also work at Cohere at the moment. I mainly work on reward modeling there. And on the side, I have an interest in tokenization. Primarily, I think I saw Enric Karpathy talk about glitch tokens and solid gold Magikarp. I was like, how can I break all the models? It'd be really fun to break all the models. And so that led to my first publication in machine learning. I was previously a computational biologist many years ago, actually. And led to me to meet this community and got more interested in all sorts of aspects of tokenization. More recently, thinking more fundamentally about, hey, why are we using UTF-8 at all? Why is that our base unit for language models? And I also have a Substack where I sort of take apart all the OpenAI regular expressions and how they fail in all sorts of different ways, and how models break. And I guess the main thing I would like to see more of is, well, I guess less of, is to have people copy OpenAI. Like just look a bit closely, what do you actually want yourself, instead of blindly copy what other people have done, which may not be suitable for your purpose.
Yeah, very fair.
Hi, everyone. I'm Alisa. I'm currently a PhD student at the University of Washington. So the future of tokenization that I am most excited about right now is superword tokenization to contrast with subword tokenization. So the key idea here is that you can capture common sequences of words into single tokens. And this can be semantically nice because we have a lot of multi-word expressions, but empirically it improves compression a lot. So you kind of get to gain benefits at training time, like seeing more raw text for the same training token budget, for instance. We've also done we have 3 papers at this workshop led by Brian and John, who are also here. So we've also studied how language models are robust to non-canonical tokenizations and how to convert tokenizer-based language models into byte-level language models at inference time without any additional training. Right, okay, there are a lot of interesting problems to study in tokenization, like a lot of fundamental problems. So Sander mentioned pre-tokenization. We have been adapting our pre-tokenization to like accommodate code better, but there's probably more work to do for non-English languages, for instance. I think tokenizer efficiency also like fundamentally shifts our scaling laws. I think that's a very interesting empirical question that has bearings on like how we develop language models in the future. But people are just starting to realize the interaction between tokenization and scaling laws. So those are just some examples. I think there's a lot of interesting work to do in this space.
Thanks.
Does this work? Okay. I'm Albert. I'm a professor at Carnegie Mellon and also chief scientist of a startup called Cartesia that mostly works in audio, but in general architectures. I'm most well known for work on architectures, just general, sequence model architectures that can be used anywhere. I don't primarily work in language, unlike I think everyone else here. In fact, I don't know a single thing about tokenizers. I think I'm invited as if you saw Yuval's talk in the morning, there's what was it, the beat 'em join them, fix them, or something. I think I'm here as the beat 'em person, but yeah. So I guess I generally, I mean, I'm here also to learn about tokenizers. The only thing I know about them is that they'll be dead soon. I'm wearing black today to mourn the loss. But I think in general, what I hope to see is, I mean, my philosophy toward AI is in general, things should be learned end to end. Our models should be able to learn better patterns and abstractions that we are like better than what we as humans are able to create, and the less engineering you do, the better. There are some really hilarious, artifacts that happen with tokenization, like these what do you call it, pre-tokenizer regexes are pretty interesting. And yeah, so I don't actually know what's going to happen, but I think there's a lot of interesting work to be done in that space. Yeah.
Awesome.
Okay, so hi everyone, I'm Yuval. I'm a assistant professor at Ben-Gurion University in Israel. And I gave the talk this morning. So if anybody wasn't here, I'll give like the quick recap is, well, first of all, I work on I think everything in tokenization. So the inference, the vocab building, the post tokenization models. I have some work on that. Analysis, benchmarking, everything. And like my two main take homes from the talk this morning were one, that I don't think we're doing enough to try and improve algorithms for building vocabularies. BPE and Unigram are both very, very rudimentary or naive. So this echoes what Kris was saying. And there's like definitely not enough work in that space, and we should maybe exhaust it before we kill tokenizers, which is a goal that I can get behind. Like I'm not completely averse to the idea. I'm not married to tokenizers, but like it's we should maybe try new stuff that is within the paradigm first. And number two is to put a lot of emphasis on evaluation. So we're not like the current process for evaluating tokenizers is like abysmal. It is not either. You have to train a full model end to end or not end to end, but like the full pipeline just so we can evaluate what your tokenizer is doing. Or you need to rely on these intrinsic metrics that for now I think are not well developed enough to give you a good sense of how well your tokenizer is going to perform. And this is, it really puts the whole research sub-community behind, because we're not in a position like regular engineers or researchers who can easily iterate on their ideas and keep improving without having to rely on very long pipelines for that. So that's
Perfect. Well, thank you all for being here. I guess my first question I'm going to pose is jumping off of that a bit, perhaps. We have seen 30-some papers presented today and many more previously, which have tried to make extensions to BB, Unigram, all of these things. And yet most LLM tokenizers remain fundamentally based on these. What things do you think are keeping the largest models from pivoting? Kris.
By keeping the largest models from pivoting, what do you necessarily mean?
I guess I mean why. Oh, I have knocked something over. Why do you think that the large models trained by, say, the large tech companies, which we all know, I'm going to remain nameless for, but why do you think they're still fundamentally BPE or Unigram-based systems? Why are we getting, say, one single line in an archive paper about tokenization suggesting there's not much change, or an API that seems to be using the same tokenizer from iteration to iteration and only changing, say, the pre-tokenization regex?
I have an answer to this. So hands up, anyone in this room who's ever used the Hugging Face tokenizers library?
Mm-hmm.
Hands up anyone who's ever been frustrated with the Hugging Face tokenizers library. I think there's a significant overlap there.
Yep.
I think to answer the question, I think unfortunately most progress in ML is gated by the software tools that we have to use ideas. And one of the strong claims I want to make, and I'm sorry if there's any maintainers of these frameworks listening or present, is that I think there's significant, how do I put this, significant user frustration with the state of the the state of the tools that we have to do tokenization right now. And I don't think that's a particularly controversial statement. Unfortunately, we have a lot of lock-in behind those tools. For example, my company, we release our models through Hugging Face. And because of that, we're sort of gated into using their tokenizer interface, their tokenizer library, because if anyone wants to call our models, download our models from Hugging Face, they have to use the Hugging Face tokenizers library. And so, like, why don't more people explore these alternative tokenization methods? It's because they don't really play well with the dominant sort of software libraries that there are. I mean, I'd love for there to be more exploration in this space, more people with better ideas, people come up with better algorithms. But there's such like strong pressure behind the tools that we use that it's very difficult for, especially a large incumbent, let's say, to adopt new ideas unless it's like quite low friction. And so unfortunately, I think at least part of the answer is not scientific, but it's just sort of like sociological, unfortunately.
Fair enough. Yes, go for it.
So I have to somewhat disagree with Kris. I don't think the reason is purely because of tools. Otherwise, I mean, Cohere's model could use a regex later than 2017. But there is something, I think, conservative about training foundation models is that they're really, really expensive. It's a really, really fast process. Like the last 2 years has been like insane. Once your first foundation model stops training, the next one starts, and there's not a lot of time and the people to do that exploration. And there's a risk to switching. So like, the previous thing is not perfect, but the risk is not that high. The edge cases versus switching to, a so-called tokenizer free method, which has like 15 moving components. It's really exciting, but maybe after 3 months, it will just reveal an edge case to which now your company is dead. Like all your pre-training model is gone, and all the competitors have released a new generation of model, and you're 6 months behind, which I think is an eternity in this field.
I'm not going to comment on the previous debate, but I think one component here is the coolness factor of working on tokenization. So I think it's not very cool. And I think a lot of people who develop
allow the room to react to that one.
No, okay, I think there's a lot more, regardless of whether you think the future is tokenizer free or tokenizer based, we simply haven't explored the potential of tokenizer based methods. That's exactly what Yuval was saying. And I think part of that is that, if you talk to people, everyone agrees that tokenization is very important. It literally controls the representation of text that language models learn over. And it's very easy to see that some encodings will be easier to learn over and others will be harder. But at the same time, people don't really, you can be a great language model developer and not really know how tokenization works. And that's because the way that we've allowed that, right? It's just fine to not think about tokenizers very much. And I think if we collectively improved literacy about tokenization, maybe that is partly limited by tooling. I'm not sure if that's the only reason. Then there's a lot of work to be done. And I think a lot of people would be interested in the problems there.
Yeah, fair enough. Yeah, go for it.
Okay. I had a lot of thoughts listening to this, but I probably forgot a lot of them. So let me try to remember as much as I can. First of all, I think one thing that we should define up front is the word tokenization seems very overloaded. I'm not sure I really, understand it or know all the definitions myself, but at the very least, I think it can be used in different ways. For example, on some level, everything has to be tokenized. If you're working over discrete data, those are always tokens. If you're using byte level tokenization, that's tokenization. So that's definitely true. I think a lot of what we're saying by when we use the word tokenization here, it's about the whole pipeline, which includes especially the segmenting algorithms like BP or Unigram. And maybe we should be more specific when we're talking about this, but hopefully, in general, it's clear. Okay, so yeah. So now I think that one reason why it's still around is for sure kind of this just the ingrained legacy pipelines and so on. It is very expensive to try new things, and it makes a lot of sense for the question is about the frontier labs, right? To be conservative. So I think that's true. One thing kind of related to what Kris was saying as well about like the technology or like the tooling around it, is that it extends not just to like the libraries we're using, but to the other building blocks that we have at our disposal. And I actually think, for example, one reason why it's been really difficult to create a good model that works over like finer grained data than BPE tokens is simply that transformers don't work that well there. So this is like one of the subjects of my research. And in our paper that has been trying to operate over finer grained data, for example, we found that the alternative models that I think people don't understand very well and also are conservative to adopt actually are pretty crucial as ingredients there. And this is just one example, right? But like I'm sure there's many other things that kind of are just around because that's the way it's been done and haven't really been questioned and so on. And then I think another big reason is also just that people, I think, don't like a lot of this is intuition driven about how much you think it matters. And ultimately, like I think the prevailing attitude that I've gotten from the community is that tokenization, as in like BPE, has like a lot of edge cases, and it's kind of like annoying to work with, and it's ugly. But we believe that it will still work if done the right way, or it's just like it's not worth the effort to like get rid of it. And so I think that really is maybe the main reason. It's that like I don't think anyone really had the conviction to be like, I really think that our models are going to get better and this is the right way to do it, and really, really invest heavily in that because it's really non-trivial. So that's the final piece is like, why is it still around? I mean, it just takes a lot of research to figure it out. Me and my students and my company Cartesia, like we invested quite a lot of resources into it. And does that really make sense for people to do that sort of research? I'm not really sure. It's partly just because like I'm unhinged, as people call me, and I decided that we just needed to solve this. So yeah, and then like it required a lot of, I think, a new machinery and ideas that were all entirely my students, to be clear. By the way, they're around if you want to talk to them. And in order to do this, right? So I think that's actually like, to me, that's one of the biggest reasons as well. Okay, I think that's enough for now.
I don't want to add a lot. I'm mostly in Kris's camp. I think it's mostly sociological and like habits. So people are used to what they like working with, and if they're not like, if this is not a topic that's very interesting to them, then they're not going to take the extra time to delve into it. And like I don't share the sentiment that you said you heard from people that it works and it's good. But I don't know, maybe like I keep like when I tell people I work on tokenization, it's always like, oh, okay, so like what is there to study about in token? So that's more what I've been hearing.
Well, in the interest of having things that we all can agree are worth looking at, do you guys have a favorite task or problem or even edge case where there is obviously a crucial dependence on tokenization, or where tokenization really does matter? Where does it really matter? Kris?
I'm sorry, I'm really monopolizing the time here. And I'm not sure if I'm allowed to talk about this, but I think enough time has passed. So here goes. I was running, I have been working on tokenizers in large labs, and at one of the places that I've worked, I got really fed up of tokenization at one point, and we had some spare compute, so I was just like, I'm just going to train a small character level model on, just to see, just to have a look. And it was really slow, and it did pretty poorly on all of the language tasks. But when I looked at like the bits per byte on code, actually my character level model, even though the context window, I hadn't changed the context window, it's still the same context window in characters as the main model had in bytes, in tokens. I was getting a better bits per byte on code than like the token-based model. So I think when I saw this, I was just absolutely gobsmacked. I was like, surely this cannot be the case. Like my context window is like a quarter of the size for code, and we know that code is like very, very important, right? And like long context dependencies in code are very important. So you're crippling yourself by quartering the context window, and yet the model is doing better. So like, I think that I really don't have any intuitions at all about how the best way to tokenize code is. And it seems like actually like characters is pretty good, or at least pretty good compared to sort of the default settings that we use for text, and then we just apply to code without really thinking about. So I think that, there are like, there's like whole domains where we don't really know that tokenization is hindering us because we've not really run the correct experiments. And I think like, I don't think it's really, there's like, the Donald Rumsfeld quote, there's a whole bunch of unknowns out there. And I think like, it's, if you have like, and because of that, I think doing research in this is quite sort of like ideal driven. You just have this feeling that something is wrong somewhere, and then you go and you dig. And yeah, sorry, that anecdote didn't really answer the question very much, but I thought it was worth sharing.
Yeah, I like it. Yeah, there we go.
I'll agree with Kris for this time. And yeah, it is very like intuition driven. It's like, this does not feel like a nice token. I'm looking at the output and I was like, I want nicer tokens, especially looking into kind of super tokens like Alisa was also interested in.
Yes.
And you look at this and go like, yeah, this has 3 HTML tags in a row and an opening tag. This is not a nice token. Maybe this has exactly the entropy that the algorithm wants, exactly the merges at frequency, but I don't like it. So how do we capture that kind of intuition into something that we could actually optimize on without me having to look at lists and manually say yes or no? That is, I think, a very, very interesting problem. Yeah.
Riffing off Kris's answer, I think in addition to code, non-English languages in general are also kind of overlooked when it comes to studying tokenization. And that sounds like a controversial answer, but I think we have some evidence to back this up. So one example I'll give is that, so we all know the chinchilla scaling laws, right? So it's telling you what the compute optimal ratio of training tokens to model parameters is given fixed training budget. And we basically have reason to believe that that ratio differs depending on the efficiency of the tokenizer. So in their paper, they're doing these scaling law experiments with a single tokenizer trained on English. So it has about, like the encoding efficiency is about 4.5 bytes per token. But it turns out that if you use a more efficient tokenizer, then basically you should have a somewhat larger model trained on fewer tokens. And we know that like if you train the same tokenizer with exactly the same setting on different languages, you're going to get a different encoding efficiency, which means that then the compute optimal language model in different languages would also be different. So that's kind of just one setting where if we kind of base our model development pipeline on English, then it might not generalize the way we want in non-English or multilingual settings.
Sorry, could you remind me the question again?
Absolutely. So what is your favorite case where tokenization really does matter? And if you don't have one, that is fine as well.
Never.
All right, mic drop.
Right. So I'm gonna go for the multilingual angle as well, but not in the sense that Alisa was saying, but the thing that I presented in my talk. So the fact that languages are inherent, some languages are inherently incompatible with a lot of preconditions or
Fun concatenative assumption.
yeah, assumptions that we make for the tokenizers, and this would also apply to token-free ideas. So working around them, or using data from those languages to construct better algorithms or better inference techniques is kind of the trick that I'm after. Not so much like using the linguistic-based engineering to solve this. I don't think that would solve everything. And so, I mean, we have examples in the findings of ACL paper for next week that show specifically how the Hebrew case harms the concatenative tokenization. So I urge you to read the paper, at least that final section. And I'm pretty sure that there's a lot more where that came from, and like there are more kinds of like non-standard languages and scripts out there, and we got the question on Chinese, and like there's so much that is not being explored in a satisfactory manner.
Yeah, fair enough.
I'm gonna elaborate slightly.
Excellent, sure.
Okay, let me elaborate just a little bit. So I think that the question can be interpreted in multiple ways, and one is like, where now do you see concrete benefits from using tokenization? Where again, I assume we're talking about things like segmentation algorithms. Whereas B, like, where might tokenization be fundamental? Right. So I think that there are a lot of concrete reasons why using tokenizers is obviously helpful now. I mean, for various reasons on compute efficiency or representation, yada yada yada. What I mean, and the direction that I work in is basically from a more philosophical stance of just I don't even, without even needing to know all of the reasons why these things help or not, I just always believe that there's no reason why we need to handcraft this, and if we do the right thing, hopefully, like all of this should be able to be learned. Hopefully, better things that we can handcraft.
Yeah, absolutely. I guess, yes, Kris, go for it.
I'd like to actually, I do have thoughts about this because when I used to tell people I wanted to character level models, like there was this like one objection that kept me up at night, which is that, like, let's say I develop a really great long context model and I can handle characters super well. I can handle the context length expansion necessary for character level models. Why couldn't I just put tokens back into that and like get much more context window for with the same model? Like somehow the universe, your favorite deity, is giving us compression for free with a tokenizer. Like, why would we not take advantage of this?
Yeah. Well, the answer to that is, I mean, so one of the things that we're trying to show in the paper, I guess I didn't explicitly say that the model that I've been working on is called the HNet that my students did, and the idea was that not only do you want to make something that can do stuff over characters instead of tokens, but that you can compose. So what we found, I think, and at least whether or not this is true now, it's certainly something that I believe will be true, is that if you basically create like an end-to-end hierarchical model that replaces tokenization and scales better than an explicit like BPE segmentation followed by a tokenized LM pipeline, then yeah, you can ask the question, why not just apply that on top of tokens instead? And yes, you can, and it would do better. But it would have been even better to just train a two-stage hierarchical model on top of the characters instead. So like the first stage kind of represents the first tokenization, the second stage makes it hierarchical again, and indeed we find that does scale better. So I think at the end of the day, it's just all about like, sure, somebody may have handed you this compression thing, but what would you say, like if God handed you these tokens and said they're the best, but I don't believe in, well, I think our models will learn something better.
You think rather than God giving you compression for free, it's like a deal with the devil that we're paying for later?
My GPUs are God. They will find something better.
I want to actually add to Albert's point. I think that there's something that even I missed until today. I talked to Dan from Apple somewhere here, so thank him for this like realization. That something underlies the idea of tokenization being at the front of the pipeline, in that you can always trust that there's a gold, there is somewhere there lies a gold segmentation for any word or any kind of string, maybe in context, maybe out of context, but you can set it to something that's really good, and then your model can take care of the rest. And it kind of follows a linguistic or morphological idea that meanings are stored in certain ways or in units that can be like statically stated. Okay, so there's morphemes, and it's good. Like if you have that, then that's all you need for good language understanding. But that maybe we've like the NLP has progressed to the position where that's not all that matters, and there are other considerations that are also just as important, or maybe even more, in terms of, well, maybe compression, or maybe I gave the example of like you might have a 6 or 7 word phrase that is composed of many different morphemes inside it, but like it doesn't really matter. Like even if it's compositional, like that's not what adds to the understanding of the entire document, because it's some kind of like a boilerplate phrase or something that's like not interesting to model. So you can just if you treat that whole thing as one patch or token or sigma or whatever, then you're going to be better off. Like if you don't give that the real estate in the transformer sequence, etc. So I think that's maybe a switch that I'm in the middle of processing like this in this very day.
Fair enough. I have a, oh yes, go for it, Alisa.
Okay, since we're using the words end-to-end a lot, I just want to make
Yes,
a quick
good, yes.
comment about UTF-8, which is also that it didn't fall from the sky. In fact, it's no less heuristic than BPE tokens, which are actually learned from data. But UTF-8, so for those who don't know, it's a mapping from Unicode characters to variable length byte sequences. So for instance, English letters are 1 byte each. Russian characters are 2 bytes each, Chinese, Japanese characters are 3 bytes each, and then Unicodes can be 4 bytes, or like sequences of emojis, sorry, can be 4 bytes or more. Anyway, the point is that like it was invented by some guys in the 1990s, and it happens to be the most available encoding of text, but that doesn't mean that it's the best for learning language models over. And there are a lot of like reasons why we would think that UTF-8 is suboptimal. Like one thing is like disparities over languages. If you encode like different languages with in UTF-8, there's like some languages are way more efficient in bytes than others. In fact, almost all languages are less efficient in bytes than English is. And yeah, I really agree with what Kris said earlier, which is that tokenization gives you compression for free. It's possible that you can, like in principle, it's possible that you get better modeling at the character level or the byte level or something like that. But you can't escape the fact that like for the rest of time, your language model processes, like even on the 10 millionth time it sees the word the, it's like, oh, that's a T, that's an H, that's an E. And maybe that's worth it. Maybe like with infinite compute, that's worth it. But it's not clear to me why we wouldn't get that compression for free.
Love that. Thank you.
Anyways, well, I think the compression is not for free because you get, okay, I'm just repeating myself, but I think there's some other good points here. So I agree that the standards we use, like UTF-8, are completely arbitrary. And as I said, like tokenization can refer to different stages of this. And I guess like my more narrow stance, which I think is more defensible, is that things like BPE and I think Unigram and these other ones all occur over some base vocabulary. And I believe that we will always get better models by operating over the base vocabulary instead of over the merges and whatever segments that these algorithms give us. Now, then there's another question of like, what is that base vocabulary? And that's another question, I think, that I think design there does matter. I think, so I was talking to Sander earlier, he had a nice paper at this workshop about, I forgot what it was called actually. But, okay.
Oh, yeah. It's script DP.
Yeah, well, you should talk more about it in a second, but I was just gonna say that I think that like, it basically, my understanding is that it basically provides much better atoms in the sense of like what your, like the base units that you're operating over are. I think that does matter. And if somebody wants like a free follow-up, I'm pretty sure if you train an HNet over that, it's gonna be soda. Yeah.
I guess a follow-up that I personally would like to ask all of you. So we talk a lot about what is a vocabulary for a particular model, and for these like tokenization free, still operating of course over tokens, or dynamic or hierarchical models, obviously at some points in the model you're acting over a very different vocabulary, potentially a non-discrete vocabulary. A lot of the things that we're talking about here are measures to evaluate tokenizers on discrete vocabularies. What are potential drawbacks, or what do you see if you're building a more open or dynamic vocabulary in terms of our ability to evaluate them? Why is this part of why we're not seeing a move towards more dynamic or tokenization-free methods? Or what thoughts have you on this space?
Okay, I'll just start here. So I think the first reason is just that it was like technically really hard. So we'll see what happens after this. You know, who knows? Maybe nobody's going to use it in a few months. Maybe it's going to work and everyone will use it. But then there's actually like a lot of technical challenges as well that I think will also hinder adoption of these things. In particular, I think more on kind of the practicality aspect and the engineering, the infrastructure. So you know, there's a lot of kind of obvious challenges, including things like your sequence lanes may be like very dynamic and variable. You're going to run into kind of utilization problems on your GPUs. You may get random out of memories if you hit some string that's like hard to tokenize and you have coarser chunks, right? There's all sorts of these things. It's going to be like MOE, but probably even a little bit harder in terms of the implementation difficulty. There's things like inference speed. I think I'm not actually sure what's going to happen there, but for example, if you're trying to decode characters or something that are, you know, like smaller units than tokens, you may just have more overhead that may prevent you from reaching the same kind of decoding speeds. So these things, I guess, you know, one can turn this and say that this is actually an artifact of like, if you're handed free compression, you should take it. So this may be one way of viewing that. I think you will get better performance, but you will run into kind of these technical and like engineering challenges.
Yeah, I was asking your student earlier as well. It's like, how do I know if my input is within the context length when I'm sending it to your HNet deployed on a server? With many models, you can like download the tokenizer, or it will send a request and say, no, your model is 1,100,000 tokens. This is too long. You should do this thing to make it shorter. So I think that's one challenge. So like, I don't know how long my input is without downloading and running an HNet locally. And the other one may be in the decoding, there will undoubtedly be edge cases that only work or only show up when you deploy this to 1 million customers and they use it every day. And maybe there'll be like infinite repeat generations, as you see in normal language models with decoding. And these things don't always show up at small scales and at benchmarks, but when you have a lot of customers and they use your models, they will suddenly ask you to fix them, and you might not have any idea how to.
I want to maybe, I don't know if expand on that or go back to Liz's question, or like I think that one consequence of moving to an end-to-end system like this is that we're gonna stop talking about evaluation of tokenizers, which nobody's talking about anyway, but to talking about interpretability. Like this will basically be offloaded onto the interpretability people or the explainability, and that is like we won't have any place where we can intervene other than to run like these explainability experiments, which I'm not sure if it's like good or bad, but like I think that would be what this entails, because you can no longer like control this part of the pipeline because it's not in pipeline anymore.
Yeah, fair enough. I guess I would like to quickly poll, though I guess many of the folks on our panel are typically working on text input. So obviously, we have some works here on image, speech. It is the case that these have typically had very dramatically different tokenization schemes in the past, though there's some convergence towards, I don't know, discrete cobooks, all of this. But what do you see as things that may or may not apply if we wanted to take, the things that we've been talking about here to something that is fundamentally continuous, as opposed to like, yes, of course, there are various units that we've all talked about for text here, but speech, for example, we do not necessarily have a set of BPE or bytes or characters as our input.
I think the fundamental problem that tokenization in any modality tries to solve is unsupervised structure discovery. And this has been a huge unsupervised machine learning problem since basically the start of machine learning. And we have a good set of heuristics for what makes good sort of like unsupervised structure discovery. I mean, when we were back when we were doing probabilistic ML, I mean, I could bore the pants off you with the inside-outside algorithm if you want. This is like all stuff from 15 years ago. But like, I think that like, we have a toolbox. We have like a well-developed set of methods for doing unsupervised structure discovery. And I think, we're kind of like very myopic in terms of like BPE, if you evaluate it as an unsupervised structure discovery algorithm, is like incredibly basic. It's really basic. It's honestly like the first thing that you might think of. And there's a lot of failure modes about BPE that like, if you read the unsupervised structure discovery literature, you'll realize that, like, of course it's going to fall into these problems. But BPE is nice because it's really fast. Honestly, that's sort of like, it's really fast and it's really simple and the algorithm's really easy to understand. And that's why everyone uses it. Like Unigram LM is a bit better, I think. It's not clear to me why it's not more widely used, apart from like, the risk of changing from something we all know and love into something a bit new. But I mean, like, I think like, like we have like this unified language to talk about the kinds of things that we would like to do across all modalities. And I think, there's a wealth of literature out there. And I think if anyone here wants to develop new tokenization algorithms for any modality, like, I think there's a lot of relevant literature out there. There's a lot of good ideas that you can just pick up, that are just lying about, begging for someone to pick them back up.
I think there's definitely analogies between text tokenization and image or audio tokenization. I haven't worked on those, but I have friends who do, and I think so. Like, I think the main difference is that for them, tokenization is like lossy, right? And for us, it's kind of lossless. You can always get back the sequence of text that correspond to a sequence of tokens, but you can't do that for audio or image. But the analogies are like, I hear that intrinsic evaluation of tokenization is really difficult. You have intrinsic measures that you would expect to correlate with downstream performance, but they don't. So for one example is like compression. Another example is like whether you can, like how much of the image you can reconstruct from the tokenized image, for instance. Even though you can reconstruct more of the image, that doesn't mean it's a better tokenizer. And so I think those problems are similar. And fundamentally, it's about how you want to encode the data that you learn over. So I think it's the same problem with very different techniques.
Yeah, I think I agree with all the answers here. Basically, like one of the reasons why, like for me, one of the reasons why I was interested in tokenization in text, even though I don't consider text like my primary domain or anything, is because to me, finding ways to circumvent tokenization actually represents just new methods for doing unsupervised structure discovery, as Kris put it. And that's what I was really after, because I feel like that's really at the heart of machine learning. And hopefully these will then be applicable to other domains without bespoke methods and modality-specific techniques. So it remains to be seen whether these newer techniques will work or not, but at the very least, that's kind of the direction that I was hoping things would go in.
Fair enough. If I can ask a quick follow-up from the Dory. Everyone, please feel free to submit questions to the Dory. We will also have an opportunity to stand up and ask questions with the mic too in a second. But if you would like to anonymously or for whatever reason not have to do so, please put it on the chat. So I guess one question might be, what is holding you or others, do you think, back from actually making a multimodal tokenizer as opposed to separately tokenizing text, audio, and images for our multimodal models? Is it simply tooling? Is it infrastructure? We often have, slightly different setups for each one of these, but,
Like, to me, it sounds like very far downstream. So, I mean, what would a multimodal tokenizer look like? That it can, a picture of a dog and the word dog would be the same token or something?
Oh,
and
well,
that feels like something that needs a lot of pre-process. Like,
fair enough.
you would have to have a whole full token, like transformer before that to just get to the tokens.
Well, I guess since I have a
But
microphone.
maybe I don't know what they meant. So
I guess what I mean by that, for example, there was a brief period where we were training a lot of speech language models by aligning separate speech and text models. They, of course, have different tokenizations. You end up with a bunch of fun things where you're just simply trying to compress audio sequences to match text and vice versa instead of potentially jointly adapting these and actually training with the downstream objective of doing speech and text together in mind. And so I was just curious if you guys have thought about this. If not, someone please work on this, get back to me. But yeah, why haven't you or others done this? Or is this just because this is my particular pet interest that I'm thinking of it?
Having observed training of multimodal models, typically the issue is we typically have widely diverging amounts of data for each modality.
Yep.
And this makes it very hard to jointly train, especially because we have very little aligned data across all of these modalities. Like, like as you might imagine, text really dominates the raw sort of like bytes of data that we have to train. So because of this data disparity, it's hard to run like end-to-end training pipelines. Often, like there's some amount of capability merging that happens because of this.
Mm-hmm.
Yeah, and so like one reason is we'd like to if we could, but it's just difficulty.
That makes a lot of sense. All right, I am going to quickly scan the Dory, but with about 15 minutes to go, if you want to urgently ask a question, because we have a limited set of microphones, I suggest you come to the center audience. If not, I will read from Dory. All right, so yes, thank you for being the first, though. Please say your name before you ask your question.
Nizar Habash, New York University, Abu Dhabi. Well, thank you all, panelists, for this discussion. I was expecting to hear something which I didn't hear, so I'm going to bring it up because, so people have been working on tokenization for a really, really long time. And you said 15 years. Actually, I know papers from 25 years that basically, from the era of statistical MT, for example, where tokenization was shown to be quite important in those days. However, its importance goes down with more data you get. And in fact, low resource language pairs, don't needed tokenization to kind of perform better. Languages that are rich started needing them less and less, and at the end it became like you don't need anything, right? And that kind of was like, at the edge of that was Word2Vec, and then we jumped into the whole different way of thinking about segmentation. So my question for you, the word I didn't hear is low resource languages. Or is it that we are in an era where the definition of low resource is irrelevant at this point? Or we don't really care about the languages that are resource. They can go and do whatever, right? So I'm just curious, is there still a place for tokenization, or is there a possibility? I'm particularly curious to hear from you of how your GPU god would be able to handle cases when there is very, very, very little evidence to start with, right? But let's suppose, there's a really, really important need to be able to solve the problem. Thank you.
All right, well, I guess I was called on. I'm not sure I've ever thought about low resource languages, unfortunately. I only speak English. But okay, what I imagine I would hope the solution looks like is that a lot of the trend that happens in deep learning is just that we want to train models that are learning the actual underlying, I don't know what it's, meaning, concepts, whatever, from data, and that transfers across tasks, modalities, whatever. I feel like what might happen is that when we have more powerful, what do we call it, unsupervised structure, discovery mechanisms, then when you jointly train them over all the languages, it will better be able to learn such segmentations and whatnot, or actually understand the language with less data, because it's seen a lot of data from other languages and kind of at least learns how to reason over language-like things in a way that might transfer. I might be completely wrong here. I'm sure the linguists are going to yell at me. But at least I feel like that's a more, to me, that seems like a more possible path toward doing this. I mean, I guess but it might also be the case that expertise will help in these. If it's really low resource, I'm not really sure.
Yeah, I've looked a lot at different scripts for the script BPE things. There's a couple of hundred different alphabets in Unicode, and some of these are really, really obscure. They are of interest to the 5 researchers that are studying this dead language, and they need to write something out. So given that in a transformer, you would need space in the embeddings to reserve it, and it takes actual GPU, RAM, and inference risk and everything, it's not worth it to ever have that be tokens unless you really want to train a tokenizer on it. For scripts, I did have the idea that having this script index thing might teach the model that this language exists, this script exists, and it might give you answers like, I don't know Egyptian hieroglyphics, but I do know that you input Egyptian hieroglyphics. Maybe you should look in these kind of sources. So I think that may be one way of supporting low resource languages, acknowledging ignorance, acknowledging that this is that language, instead of hallucinating they're all glitch tokens.
I kind of want to extend Albert's answer a bit, which is sort of appealing to some kind of no free lunch theorem. The less data that we have in a particular domain, in a particular language, the more we need to build in biases into our modeling if we want to do, to process that language. And one way we can do that is with via the model. So, we have more powerful unsupervised structure discovery architectures baked into the model that we use to process. And the other, I'm sure you're aware of this, is people used to do unsupervised segmentation. Sharon Goldwater 10, 15 years ago used to do a lot of this. And morphological, people hand wrote morphological analyzers for particular languages. There was actually a paper which I worry was lost during COVID. It kind of came out during COVID, but they did something really, really interesting, which is they tried. It was the proceedings of a summer workshop, one of the Jelinek workshops at JHU, and they tried to do language modeling of Inuit. And for people who are unaware, Inuit can express 20-word sentences using 2 words, because the morphological processes in Inuit compound words to such an extent that a single word can be an entire verb phrase in English. And so, like, you know, how are we supposed to tokenize this? This is the extreme case. And you know, in practice we could with the tokenizers that we have, because we just split apart the words into the bits. But it turns out that, like, you know, if you do the standard language modeling pipeline on this, A, there's very little data, so it doesn't work very well, and B, like, the tokenizer just falls over. Like, it doesn't analyze the language sufficiently well to be able to give you units that let you model the language very well. And then they went back and they were like, okay, we'll write an analyzer. We use a morphological analyzer for this. They did the best they could to actually break down the big compound words into individual components, and then ran a language model over this, and they got better performance. So if you really, really care about, like, a particular language, a particular domain, you know, like, a little bit of legwork is going to get you a long way. Like unfortunately, giving up some of this end-to-end sort of, like, and baking in some of your knowledge is going to help. This is not scalable, though. Like, suppose I want to serve 70 models with my language. I can't write a separate morphological analyzer for each language that I want to train. I want to serve. So, like, you know, there's this tension, I think, between like squeezing out every inch of performance possible on every language, and then being able to serve as many people as possible by serving as many languages as possible. So I think I couldn't tell you how to solve this dilemma, but, like, you know, it exists.
A quick plug, that was JSOL 2019-2020, working on Indigenous languages of Canada. And another fun fact is that brings up one of my favorite pet problems, the fact that we do not necessarily have uniform or regularized Unicode representations for given scripts. So a lot of the assumptions we've just baked in this discussion would not hold as well. Yeah, sure. Yes, absolutely.
You know, your answers are great. I just want to kind of point out a blind spot that often we have in the West generally when it comes to working with languages that are less resourced, is that, and all your answers actually implied that bias of, oh, how can I understand what they said, as opposed to how can I talk to them in their language, right? And in analysis generation, well, in the old models, they always put them, like, on different edges of a pyramid, and they look symmetrical. They're completely not symmetrical, right? It's much easier to analyze because you have a lot more flexibility to fill in the gaps using all the resources that you may have. But to actually generate properly, you know, complete sentences in Inuit, right, requires the linguist, the analyst, etc., to provide you with, you know, sources to create synthetic data, you could say, to add, etc. But it requires something that is atypical, because this is not a natural kind of, I just flip the model and then everything works out.
Thank you for that. All right.
There was one other unhinged opinion I forgot to express earlier, which some part of this conversation reminded me. But there was a talk earlier today about a pixel, like learning stuff from pixels, and that's like the ultimate, you know, tokenizer-free representation. It is pixels all the way down. And eventually we are going to have models that can operate over that space. There's, like, meaning that's conveyed by, you know, your font and other things and whatnot that you can draw from that. And that might be the only hope you have for, like, you know, if we discover a new lost language that nobody can understand, the only way that we can understand, like, the linguists, I mean, they're going to help, of course, but, like, I think you probably just need to read the pixels with your super powerful AI that's understood every single language in the world and hope that they can find patterns that we weren't able to find.
I'll add a somewhat random fact. Is that for the native Canadian,
I love it. We're at the random fun takes.
Yeah, the native Canadian script, I think the most common characters were the triangles, which are used as play buttons by a lot of people.
Cool. Okay. Actually, there is an anonymous question. Oh, yes, we have a hand. All right, come on up. And then I will... Feel free to walk at your pace. We appreciate it.
Just because we get into the sort of crazier ideas part of the talk.
Yeah,
I just would like to hear you guys sort of semi-seriously discuss. A fun idea I had is, like, what if we're just training an autoregressive model on, like, bytes? Just all data is just bytes. Like, why not? Because like pixels is great, but it doesn't do like audio, right? So
Well, it could, spectrograms, but that's aside.
UTF-8?
Yeah, we talked about UTF-8 and our dislike of it. Our dislike of it. Yes, but that's a text. That's a way to get to bytes. So what does the range of 2 to 255 have to do with anything? Why bytes?
Like Thomas Mikolov, whose name has come up quite a few times. Thomas Mikolov had a difficult second album period post Word to Vec. And at one point, he was working on this. He thought, like bytes are the universal interface. We'll train a model on everything expressed in some kind of encoding in bytes. Encodings are all poor, all of this stuff. This was in 2017. I heard about this in 2017, and I just think the compute resources weren't at that time just weren't good enough. And so sorry, that wasn't an answer to your question. That's just a random anecdote.
We are down to our final minute of the panel, and given that I am going to attempt to not keep you all here forever, I'm going to have each one of you just go down, and if there's any one thing that you wish you could have had a conversation about, or what would it be? If someone were to come find you in the hallway to ask you this, what's the one thing you want to talk about that haven't throughout the day?
Evaluation.
Cool. All right.
I think there are two questions: the best architecture and the best encoding. They're different questions. The best outcome is like in the Cartesian product of those, but we don't treat the problem that way.
Nice.
Yeah, I think we've actually covered it. What's a good token?
Okay. Yeah.
I would love to use more powerful algorithms than BPE and see whether we can actually make the model better. My hot take that I've not brought up is tokenization is just language modeling. Compression is loss. Compression is literally loss. I learned all my machine learning from David Mackay's book. He makes this point very clearly. And so, I think we should take this analogy seriously and use really powerful language models as tokenizers.
Nice. Albert?
I can't think of anything in particular, but if you find me in the hallway, I'm sure I'll talk your ear off.
Excellent. I think that's a perfect way to end. So let's thank our panelists.